Hello, 7th graders. Your next video is on section 8.4, which is data variability. We're going to start out with box plots, which in the past have also been called box and whisker plots. And I'm going to go over some terms first for those. The box plot, it uses 5 points on a number line to summarize a data set. And I'll go through what the points are in which column. The interquartile range is the difference between the upper and lower quartiles. And again, I'll show you that on a drawing here in just a little bit. Variability, it tells how much data is spread out. So it's like the range, basically. You could call variability the range of all the information. So it'd be the highest number minus the lowest number. All right, so let's take a look at this box and whisker plot that I have drawn here and look at the terms that go with these. So I have your 5 dots there. When you make a box and whisker plot, you never put the dots, the points on the line, you put it above the line because of all the things that you need to draw with it. And so the first point that we have there, you can see right here, is a 1. And so that is the lowest value of all of your data. This one over here, the 5th dot, is always your highest value. So if you take your highest minus your lowest, so you'd have 10 minus 1, so your variability or your range would be 9 for this information. The lower quartile is on 4. The upper quartile is on 8. And those are always the 2nd and 4th dots. This one right here is always called the median. There should be a line drawn through it like that. So the 3rd dot is always the median of all the information. So the median for this information is 6. Okay, and it doesn't even really matter what they're talking about, but you should be able to figure out what the dots mean. Okay, the box is always drawn around the 2nd and 4th dots, and then a line is drawn through the median. And then you see these lines drawn out right here. Those are the whiskers. And so if you have a really long whisker on one of them, it would mean that you have an outlier. You have a number that's way higher or way smaller than all the rest of them. All right, so here I have drawn another box and whisker plot, but this is a double box and whisker plot because I'm comparing 2 different types of dogs, an Australian Terrier and a Boston Terrier. And so I have all the dots drawn here, the points, and we're going to take a look at them. So it says a veterinarian collects data about the weights of the dogs she treats. Compare the IQRs, the interquartile range is what that means, IQR, of the data sets to draw an inference about the dogs. Okay, well, interquartile range is really easy. All you have to do is take the upper quartile minus the lower quartile. So the 2nd and the 4th dots, if you were paying attention to what I just went over. So for the Australian, the highest dot is on 14 right here, the higher extreme, the higher quartile. The lower quartile is on 11. So I'd go 14 minus 11 is 3. And over here for the Boston, the upper one is on 20, and the lower one is on 17. And so the interquartile ranges are the same. Okay, they're both 3. So it says the IQRs, the interquartile ranges, are the same. So you can infer that the weights of both dogs vary by the same amount, right? They vary. They have the same interquartile ranges. There's still more that we can talk about with that, though. So here it says, compare the medians of the data sets in example 1 and use the comparison to draw another inference about the dogs. Compare the medians. Okay, well, the median of the Australian, you can see, is right here at 13, right? So you have 13 pounds for Australian Terrier, and the Boston, you're looking at the 3rd dot is the median, so it's at 19. Okay, so 19 pounds for So Australian median is 13, Boston median is 19. So here's what you can infer from that. You can infer that on average, the Boston Terrier is a bigger dog than the Australian Terrier. Well, that would make sense, wouldn't it? Go back up here and look at the box plots. The Australian's information is all down here. So the heaviest Australian Terrier was 16 pounds. The heaviest Boston Terrier was 22. Well, that's quite a bit of difference. So the Boston Terrier is definitely, on average, a heavier dog. That's what that means. The next part here, mean absolute deviation. So the average distance between the mean and each data value. So when you figure this out, if the mean absolute deviation, which I'm going to call MAD probably from now on, just because it's easier to say, if you have a multiple of less than 1, so a number less than 1 indicates a large overlap in your information, and a multiple of more than 1 indicates little or no overlap. Now, it seems backwards of what you would think, but that is how you do it. So here I have commercials during 1-hour shows. So I have 32 commercials, 1 time that happened, 33 commercials, 1 time, 34 commercials, 3 times. You see how I'm reading this? 35 commercial happened, and I should have these labeled, I guess. This is station A, and this is station B. So TV stations, right? A and B. And then it tells you how many times you had that many commercials in a 1-hour show. So here it says calculate the mean of each data set. All right, so here is my calculations for the mean. So for station A, all you do is go through here and write down every single one. So I have a 33, a 35, a 35, a 35, a 36, 36, 36, 37, 38, 39. That's where I got these numbers. Add them all up and divide them by 10. Your answer is 1.2 for your MAD, the mean absolute deviation. So for station B, I add up 32, 34, 34, 34, 35, 35, 36, 36, 37, 37, and I divide it by 10. Why? Because there's 10 x's. And you get 1.2 for both of them, which is kind of crazy, but that's how it works. They have the same mean absolute deviation. So and then I can, or excuse me, not mean absolute deviation. I didn't mean that. That's the mean, right? The mean absolute deviation is what we're getting to next. So that's for the mean. Those are the means. They have the same mean. They're both 1.2 average. Okay. Let me back up. I'm getting ahead of myself. I went ahead in my notes, so I'm off. When you divide those out, you get 35 for the mean. And right here, 36 for the mean. I skipped way ahead and I did the mean absolute deviation, which is what we're going to do next here. So if you divide that out, you get 35 and you get 36. So they're pretty close to the same. So then if we move on to the mean absolute deviation here, I have 2 different sets of information here. And so for the mean absolute deviation, in parentheses here, I wrote you take the total distance divided by the total items. Okay. So I have the mean written, and it's the same for all of them, because for station A, we just figured out that the mean was 36. For station B, we figured out it was 35, so I wrote 35 all the way across here. Then I just wrote in the commercials, just like I had them up above, right? And then the distance is how far the mean is from how many commercials were counted. So 36 minus 33 is 3. 36 minus 35 is 1. 36 minus 35 is 1, and on and on. Here, these are 0, 1, 2, and 3, because 39 minus 36 is 3. You don't do negatives for distance. You just count the distance from the mean. That's all that is. So these ones, again, I wrote down all the commercials, how many times they happened, and where did I get that from? I took it right off of this other table right here. And then again, the mean, I already figured that out up above. And so 35 minus 32 is 3. I'm just finding how far is the mean from what actually was counted. That's it. 3, 1, 1. You go across, and I just subtracted all of these, okay? So I have all of my distances for station A and station B there. So now what can we actually do with that information? We can figure out the mean absolute deviation is what we can do, which is what I had skipped ahead to on that last section. And so here's how you do it. So you add up all of these distances. So 3, 4, 5, 6, 7, 10, 12, right? So you have 12 for your distance. And how many did I have? There was 10 of them. So 12 divided by 10. So for the station A, the 1.2 is the MAD. 3, 4, 5, 6, 7, 8, 10, 12. Oh, look at that. It's going to be the exact same for the bottom one. So they both have 1.2 mean absolute deviation. So what did that mean? If you go way back up here and look, a multiple of more than 1 means little or no overlap. Okay. So then down here, the very last thing we can do with this, it says what multiple of the MADs, mean absolute deviations, equals the difference between the means. And in parentheses, I wrote how you're going to figure that out. You're going to take the MAD times n, and that's going to equal the difference of the means. So the MAD, which we just figured out right up here, is 1.2. So you take 1.2 times n, and that's going to equal the difference of the means. Well, the means were 36 and 35, right? So 36 minus 35. So 1.2n equals 1. And then I'm going to solve for n. So 1 divided by 1.2 equals 0.8. And what does that really mean? It indicates that there is a large amount of overlap between the two data sets. Okay? So I found out the mean absolute deviation is 1.2. And then I used that to figure out how much overlap I have. And there's a lot of overlap. And you can tell that just by looking at these two tables. You should be able to see that, right? This one has 32s and 34s. This one doesn't. But this one has a bunch of 35s, 36s, 37. So does this one, right? 35, 35, 36, 36, 37. These are all overlaps. So there was a lot of overlap. We could have figured that out just by looking at the tables. And so that's a lot of information taken at once. I understand that. The main thing I want you to remember for next week when we come back to this, the next time I see you, is what the points mean. So if I showed you a box and whisker plot, you should be able to tell me what the points mean. The lowest value, the lower quartile, the median, upper quartile, the highest value. You should be able to figure out the interquartile range, because you just take the upper quartile minus the lower one. That should be, up to that point, should be pretty easy. You should be able to compare, like if I give you a double box and whisker like this one, you should be able to compare those and come up with some type of conclusion about that information. And then once we get down to the mean absolute deviation, it gets a little tougher, and we'll go over more of those in class, but I want you to have at least seen it before we go into more detail on it. So that concludes this video. Have a good night.